Charges in motion constitute an electric current. Such currents occur naturally in many situations. Lightning is one such phenomenon in which charges flow from the clouds to the earth through the atmosphere, sometimes with disastrous results. The flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in a steady manner, like water flowing smoothly in a river. A torch and a cell-driven clock are examples of such devices. Electric current. Imagine a small area held normal to the direction of flow of charges. Both the positive and the negative charges may flow forward and backward across the area. In a given time interval t, let Q plus be the net amount, that is, forward minus backward of positive charge that flows in the forward direction across the area. Similarly, let Q be the net amount of negative charge flowing across the area in the forward direction. The net amount of charge flowing across the area in the forward direction in the time interval t is Q equals to Q plus minus Q. This is proportional to T for steady current, and the quotient I equal to Q divided by T is defined to be the current across the area in the forward direction. If it turns out to be a negative number, it implies a current in the backward direction. Currents are not always steady, and hence more generally, we define the current as follows. Let Q be the net charge flowing across a cross-section of a conductor during the time interval t, that is, between times t and t plus t. Then, the current at time t across the cross-section of the conductor is defined as the value of the ratio of Q to t in the limit of t tending to 0. In SI units, the unit of current is ampere. An ampere is defined through magnetic effects of currents that we will study in the following chapter. An ampere is typically the order of magnitude of currents in domestic appliances. An average lightning carries currents of the order of tens of thousands of amperes, and at the other extreme, currents in our nerves are in microamperes. Electric currents in conductors. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charge particles do exist like an upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 1,022 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound, that is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are practically free to move within the bulk material. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the current is carried by the negatively charged electrons. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. In solid conductors, the current is carried by the negatively charged electrons in the background of fixed positive ions. Consider first the case when no electric field is present. The electrons will be moving due to thermal motion during which they collide with the fixed ions. An electron colliding with an ion emerges with the same speed as before the collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction for the velocities of the electrons. Thus, on the average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So, there will be no net electric current. What happens to such a piece of conductor if an electric field is applied? Imagine the conductor in the shape of a cylinder of radius r. Suppose we now take two thin circular disks of a dielectric of the same radius and put positive charge plus Q distributed over one disk and similarly minus Q at the other disk. We attach the two disks on the two flat surfaces of the cylinder. An electric field will be created and is directed from the positive towards the negative charge. The electrons will be accelerated due to this field towards plus Q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electric current. Hence, in the situation considered, there will be a current for a very short while and no current thereafter. We can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges to make up for any charges neutralized by electrons moving inside the conductor. In that case, there will be a steady electric field in the body of the conductor. This will result in a continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are cells or batteries. Ohm's law, a basic law regarding flow of currents, was discovered by G.S. Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. Imagine a conductor through which a current I is flowing and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V is proportional to I, or V equals to R multiplied by I, with a constant of proportionality R is called the resistance of the conductor. The SI units of resistance is ohm and is denoted by the symbol omega. The resistance R not only depends on the material of the conductor, but also on the dimensions of the conductor. Consider a conductor to be in the form of a slab of length L and cross-sectional area A. Imagine placing two such identical slabs side by side, so that the length of the combination is 2L. The current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab is identical to the first and the same current I flows through both. The potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs, and hence equals 2V. The current through the combination is I, and the resistance of the combination RC is equal to twice the resistance. Doubling the length of a conductor doubles the resistance. In general, then, resistance R is proportional to length L. Imagine dividing the slab into two by cutting it lengthwise so that the slab can be considered as a combination of two identical slabs of length L, but each having a cross-sectional area of A divided by 2. For a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I divided by 2. Since the potential difference across the ends of the half slabs is V, that is the same as across the full slab, the resistance of each of the half slabs, R1 equals to 2R. Thus, having the area of the cross-section of a conductor doubles the resistance. In general, then the resistance R is inversely proportional to the cross-sectional area, which can be represented as a proportional to 1 divided by A, that is the inverse of A. Hence, for a given conductor, the resistance R is equal to ρ multiplied by the length L divided by the cross-sectional area, with a constant of proportionality ρ depends on the material of the conductor but not on its dimensions, is called resistivity. Current per unit area, taken normal to the current, I divided by A, is called current density and is denoted by J. The SI units of the current density are A divided by meter square. Further, if E is the magnitude of uniform electric field in the conductor whose length is L, then the potential difference V across its ends is E multiplied by L. The current density, which we have defined as the current through unit area normal to the current, is also directed along E and is also a vector. Thus, the last equation can be written as E equals to J multiplied by rho. Hence, J equals to sigma E, where sigma equals to 1 divided by rho and is called the conductivity. Drift of electrons and the origin of resistivity. An electron will suffer collisions with the heavy fixed ions, but after collision, it will emerge with the same speed but in random directions. If we consider all the electrons, their average velocity will be 0 since their directions are random. Consider now the situation when an electric field is present. Electrons will be accelerated due to this field by equals to minus E divided by m, where minus E is the charge and m is the mass of an electron. The average velocity of the electrons at time t is the average of all the velocities. The average of velocities is 0, since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of the electrons do not occur at regular intervals, but at random times. Let us denote by 2 the average time between successive collisions. Then at a given time, some of the electrons would have spent time more 2 than, and some less than 2. The electrons move with an average velocity, which is independent of time, although electrons are accelerated. This is the phenomenon of drift, and the velocity, Vd, is called the drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E, the magnitude of uniform electric field in the conductor. Mobility. Conductivity arises from mobile charge carriers. In metals, these mobile charge carriers are electrons. In an ionous gas, they are electrons and positive charged ions. In an electrolyte, these can be both positive and negative ions. An important quantity is the mobility mu, which is defined as the magnitude of the drift velocity per unit electric field. That is, mu equals to drift velocity Vd divided by the electric field E. The SI unit of mobility is m squared divided by Vs, and is 10 to the power of 4 of the mobility in practical units, which is centimeters squared divided by Vs. Mobility is positive. Limitations of Ohm's law. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits with a proportionality of V and I does not hold. The deviations broadly are one or more of the following types. A. V ceases to be proportional to I. The dotted line represents the linear Ohm's law. The solid line is the voltage V versus current I for a good conductor. B. The relation between V and I depends on the sign of V. In other words, if I is the current for a certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction. This happens, for example, in a diode. C. The relation between V and I is not unique. That is, there is more than one value of V for the same current I. A material exhibiting such behavior is gallium arsenide. Materials and devices not obeying Ohm's law are actually widely used in electronic circuits. Resistivity of various materials. The materials are classified as conductors, semiconductors, and insulators depending on their resistivities in an increasing order of their values. Metals have low resistivities in the range of 10 to the power of minus 8 ohm meter to 10 to the power of minus 6 ohm meter. At the other end are insulators like ceramic, rubber, and plastics, having resistivities 10 to the power of 18 times greater than metals or more. In between the two are the semiconductors. These, however, have resistivities characteristically decreasing with a rise in temperature. The resistivities of semiconductors can be decreased by adding small amount of suitable impurities. This feature is exploited in use of semiconductors for electronic devices. Temperature dependence of resistivity. The resistivity of a material is found to be dependent on the temperature. Different materials do not exhibit the same dependence on temperatures. Some materials like nichrome, which is an alloy of nickel, iron, and chromium, exhibit a very weak dependence of resistivity with temperature. Manganese and constantan have similar properties. These materials are thus widely used in wire-bound standard resistors since their resistance values would change very little with temperatures. Unlike metals, the resistivities of semiconductors decrease with increasing temperatures. The resistivity of a material ρ depends inversely both on the number n of free electrons per unit volume and on the average time too between collisions. As we increase temperature, average speed of the electrons, which act as the carriers of current, increases, resulting in more frequent collisions. The average time of collisions too thus decreases with temperature. In a metal, N is not dependent on temperature to any appreciable extent, and thus the decrease in the value of 2 with rise in temperature causes ρ to increase. For insulators and semiconductors, however, N increases with temperature. This increase more than compensates any decrease in 2. Electrical energy, power. Consider a conductor with endpoints A and B, in which a current I is flowing from A to B. The electric potential at A and B are denoted by V, A, and V, B respectively. Since current is flowing from A to B, V is greater than V, B, and the potential difference across AB is V equals to V minus VB, which is greater than 0. In a time interval delta t, an amount of charge delta Q equaling to I delta t travels from A to B. The potential energy of the charge at A, by definition, was QVA, and similarly at B, it is QVB. Thus, change in its potential energy U pot is U potential equals to final potential energy minus the initial potential energy. If charges moved without collisions through the conductor, their kinetic energy would also change, so that the total energy is unchanged. In case charges were moving freely through the conductor under the action of electric field, their kinetic energy would increase as they move. On the average, charge carriers do not move with acceleration, but with a steady drift velocity. This is because of the collisions with ions and atoms during transit. During collisions, the energy gained by the charges thus is shared with the atoms. The atoms vibrate more vigorously and the conductor heats up. Thus, in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval delta t is delta W equals to IV delta t. The power loss, ohmic loss, in a conductor resistance R carrying a current I is given by P equals to V squared divided by R. It is this power which heats up, for example, the coil of an electric bulb to incandescence, radiating out heat and light. Where does the power come from? We need an external source to keep a steady current through the conductor. It is clearly this source which must supply this power. In the simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. Heat is produced in the resistor R which is connected across the terminals of a cell. The energy dissipated in the resistor R comes from the chemical energy of the electrolyte. The expressions for power show the dependence of the power dissipated in a resistor are on the current through it and the voltage across it. Electrical power is transmitted from power stations to homes and factories, which may be hundreds of miles away, via transmission cables. One obviously wants to minimize the power loss in the transmission cables connecting the power stations to homes and factories. How this can be achieved? Consider a device R to which a power P is to be delivered via transmission cables having a resistance, RC, to be dissipated by it finally. If V is the voltage across R and I is the current through it, then P equals to VI. The connecting wires from the power station to the device has a finite resistance, RC. The power dissipated in the connecting wires, which is wasted, is PC, with PC equals to I squared multiplied by RC. Thus, to drive a device of power P, the power wasted in the connecting wires is inversely proportional to V square. The transmission cables from power stations are hundreds of miles long, and their resistance RC is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for the high voltage danger signs on transmission lines, a common sight as we move away from populated areas. Using electricity at such voltages is not safe, and hence at the other end, a device called a transformer lowers the voltage to a value suitable for use. Cells, EMF, internal resistance. A simple device to maintain a steady current in an electric circuit is the electrolytic cell. Basically, a cell has two electrodes, called the positive P and the negative N. They are immersed in an electrolytic solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. The positive electrode has a potential difference V plus between itself and the electrolyte solution immediately adjacent to it. Similarly, the negative electrode develops a negative potential V minus relative to the electrolyte adjacent to it. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is the sum of V plus and V minus. This difference is called the electromotive force, EMF, of the cell and is denoted by the Greek symbol epsilon. Note that the EMF is actually a potential difference and not a force. The name EMF, however, is used because of historical reasons and was given at a time when the phenomenon was not understood properly. To understand the significance of epsilon, consider a resistor are connected across the cell, figure 3.12. A current I flows across R from C to D. A steady current is maintained because current flows from N to P through the electrolyte. Clearly, across the electrolyte, the same current flows through the electrolyte, but from N to P, whereas through R, it flows from P to N. The electrolyte through which a current flows has a finite resistance, R, called the internal resistance. Consider first the situation when R is infinite, so that I equals to V divided by R equals to 0, where V is the potential difference between P and N. Now, V equals to potential difference between P and A plus the potential difference between A and B plus the potential difference between B and N, which is equal to epsilon. Thus, EMF epsilon is the potential difference between the positive and negative electrodes in an open circuit, that is, when no current is flowing through the cell. The maximum current that can be drawn from a cell is 4R equals to 0, and it is I max equals to epsilon divided by R. However, in most cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell. Cells in series and in parallel. Like resistors, cells can be combined together in an electric circuit. And like resistors, one can, for calculating currents and voltages in a circuit, replace a combination of cells by an equivalent cell. Consider first two cells in series where one terminal of the two cells is joined together, leaving the other terminal in either cell free. Epsilon 1 and epsilon 2 are the EMFs of the two cells, and R1 and R2 their internal resistances, respectively. The rule for series combination clearly can be extended to any number of cells. 1. The equivalent EMF of a series combination of N cells is just the sum of their individual EMFs. And 2. The equivalent internal resistance of a series combination of N cells is just the sum of their internal resistances. This is so when the current leaves each cell from the positive electrode. If in the combination, the current leaves any cell from the negative electrode, the EMF of the cell enters the expression with a negative sign. Kirchhoff's rules. Electric circuits generally consist of a number of resistors and cells interconnected sometimes in a complicated way. Two rules, called Kirchhoff's rules, are very useful for analysis of electric circuits. Given a circuit, we start by labeling currents in each resistor by a symbol, say I, and a directed arrow to indicate that a current flows along the resistor in the direction indicated. If ultimately I is determined to be positive, the actual current in the resistor is in the direction of the arrow. If I turns out to be negative, the current actually flows in a direction opposite to the arrow. Similarly, for each source, that is, cell or some other source of electrical power, the positive and negative electrodes are labeled, as well as a directed arrow with a symbol for the current flowing through the cell. Having clarified labeling, we now state the rules and the proof. A. Junction rule. At any junction, the sum of the currents entering the junction is equal to the sum of currents leaving the junction. This applies equally well if instead of a junction of several lines, we consider a point in a line. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point in a line. Thus, the total current flowing in, which is the rate at which charge flows into the junction, must equal the total current flowing out. Loop rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is zero. This rule is also obvious, since electric potential is dependent on the location of the point. Thus, starting with any point, if we come back to the same point, the total change must be zero. In a closed loop, we do come back to the starting point, and hence the rule. Wheatstone bridge, as an application of Kirchhoff's rules, consider the circuit called the Wheatstone bridge. The bridge has four resistors R1, R2, R3, and R4. Across one pair of diagonally opposite points, a source is connected. This is called the battery arm. Between the other two vertices, a galvanometer, which is a device to detect currents, is connected. In this case, the Kirchhoff's junction rule applied to junctions immediately gives us the relations I1 equals to I3 and I2 equals to I4. We also obtain the condition R2 divided by R1 equals to R4 divided by R3. This equation relating the four resistors is called the balance condition for the galvanometer to give zero or null deflection. The Wheatstone bridge and its balance condition provide a practical method for determination of an unknown resistance. A practical device using this principle is called the meter bridge.